This lecture is about a very popular exploratory data analysis technique called hierarchical clustering. So I'm going to start off talking a little bit about clustering in general, and then I'll talk a lot more about hierarchical clustering in this lecture. Clustering organizes things that are close into groups. So we'll talk a little bit about what we mean by that in terms of how do we define close when we're talking about data measurements, and then how do we group things together once we've defined close. And how do you visualize the grouping so that you can show it to other people or interpret that grouping so that you can see if there are groups that you believe or there are groups that have been created using this statistical process that maybe are a little bit hard to believe or might be just due to noise. It's an incredibly important idea. So this is actually just a search that I did in Google Scholar for cluster analysis. And you can see there are a bunch of papers here, but they've been cited by thousands and thousands of people. So this is a indication that thousands and thousands of people have used cluster analysis for doing different types of analyses, and it's widely used both in academics and in the business and scientific communities. So now I'm going to talk a little bit about hierarchical clustering. It's what's called an agglomerative approach to clustering, and the reason why it's called agglomerative is because it's sort of bottom up. So what you do is you start by finding the two observations or two variables that are closest to each other, and then you merge them together into one new sort of super observation. Then using all the observations you have and the two merged observations that were closest together, then you go and find the next two that are closest together and so forth, successively putting together the next two closest things until you've merged all the things together into one big object. To perform hierarchical clustering, it requires a defined distance measure. So how do you determine if two things are close to each other? And then it also requires a merging approach, because at the end of the day we need to merge things together, and so how do we do merging in such a way that we can then merge the next two things? What this produces is a tree showing how close things are to each other that's called a dendrogram, and we'll be talking a lot more about that in the lecture. So first of all, how do we define close? This is actually the most important step in a clustering algorithm. So if you produce a garbage closeness parameter, it's going to produce a garbage clustering. And what do I mean by garbage? I mean if the clustering algorithm uses a distance metric that isn't appropriate for the kind of data that you have, if it's susceptible to different kinds of quirks of the data that you know that your particular data set have that other data sets don't, you'll definitely see clusterings that are less easy to interpret and that are less clearly represent the patterns that you observe in the data set. So some examples of distances or similarities for continuous variables, you can use Euclidean distance. We'll talk about that in a minute. You can also represent distance instead by the opposite, which is similarity. So you can actually, instead of looking at the smallest distance, you can look at the greatest similarity. So for example, you can look at the correlation between observations. You can also look at binary measures of distance. So we'll be talking about the Manhattan distance as a measurement of binary distance. You need to think really hard about this step because you need to pick a distance or similarity that makes sense for the problem that you're analyzing to be able to get a good clustering out at the end. So I'm going to start off by describing a couple of example distances. The first is Euclidean distance. So imagine that you want to know the distance between DC and Baltimore. So you have a latitude and a longitude variable for DC and a latitude and longitude for Baltimore. And two different sort of measures that you could get the distance between the two y measurements or the distance between the two latitude measurements between Baltimore and DC. You could also get the distance between the two longitude measurements, or the difference between the two x values. And some combination of these two distances adds up to give you what you're looking for, which is the distance between DC and Baltimore. And if you recall from geometry class you may have taken a long time ago, the way that you actually calculate the distance between Baltimore and DC in this case is you take the squared distance between the x values and the squared distance between the y values, and you take the square root of that, and what you end up with is the distance between DC and Baltimore. And so in general what we're going to be doing, this is in 2 dimensions, but in general what you're going to be doing is having more dimensions than that. You might have each person has 25 variables measured on them, and we want to be able to determine how close two people are. So what you would do then is you would take every single variable between the two people and you would take the measurement for person 1 and subtract the measurement for person 2 for variable 1, square it, and then add it to the difference between the two values for variable 2 between person 1 and person 2 and square it and so forth, and then take the square root. This is called the Euclidean distance and is often used for quantitative variables or continuous variables when performing clustering. Another option is the Manhattan distance. So the Manhattan distance is used often for binary variables. And what it does is, so suppose you're trying to look at the distance between this point and this point on this graph. Any of these lines actually travels the same distance by the Manhattan distance, which is just you can think of it as if this is one building and this is another building in Manhattan, New York, the number of blocks that you cover by taking the red line, the yellow path, or the blue path are all the same. The Euclidean distance, of course, is this green line here, but you can't take that because you'd be going through buildings. So what you do instead is you take one of these other paths, and the shortest one will be sort of the Manhattan distance between the 2 points. And so the Manhattan distance is actually just the same thing as the Euclidean distance. Instead of taking the square of the difference between the 2 coordinates, you actually take just the difference between the 2 coordinates and you take the absolute value of that difference. And so that it turns out that for this sort of problem, by taking the absolute value of the difference between the y coordinates and the absolute value of the x coordinates, you actually get the distance along either the yellow, blue, or red path here for the Manhattan distance. So now I'm going to show you an example of hierarchical clustering, and so to do that I'm going to generate just a really simple simulated data set. And so what I do is I set the seed so that I always get the same data set out, and then I generate x variables and y variables such that there are 3 clusters. There's sort of a cluster down here on the left, that's the first 4 observations. Then there's a cluster up here in the middle, that's the second 4 observations, and then the third 4 observations over here on the right. And then I've actually used the text command to actually label them with the numbers so it's a little bit easier to see. So how hierarchical clustering works is first it's going to calculate a distance between all of the different points. So in this case there are 12 different points that we've observed, and we're going to calculate the distance based on their x and y values. So to do that I create a data frame that has the x values and the y values for the point, and then I use the command dist, which actually calculates the distance between the points. The parameters to dist are x, that's the data frame or matrix that you're calculating the distances on. So in the case of a data frame, what it's going to do is it's going to calculate the distances between all of the different variables that you've observed for each observation. And in the case of a matrix, it's going to calculate sort of the distance between columns. And then you have to tell it a method. So in this case, you tell it that when you don't give it the default method is Euclidean distance, but you can also tell it to take the Manhattan distance and binary distance and other distance metrics. So this is now the matrix of distances that comes out. So it's missing the top half because it's the same for the top and the bottom. It's also missing the diagonal because the distance between any point in itself is just 0. And so you can say the distance between point 1 and point 2 is 0.34. The distance between point 3 and point 1 is 0.57, and so forth. So you can find the column and the row of this matrix to find the distance between points. So here's how hierarchical clustering works. It takes that distance that's been calculated and it says, okay, what are the 2 closest points on this plot? So in this case, the 2 closest points are 5 and 6. And so what it does is it says, okay, now I'm going to just put those 2 points together. So I have points 5 and point 6 are now together and have been linked. So then the next step it does is it merges those 2 points together. So the way that it merges them together in this particular algorithm is what it will do is it'll take those 2 points and it will get their average x value and their average y value. And now it creates a new point here. It ignores points 5 and 6 because they've already been merged. And it now performs the exact same operation using the merged value for 5 and 6. So it says, what are now the 2 closest values together? In this case, values 10 and 11 are the next 2 closest values together. And so they get merged together, and we see actually that another sort of link between values of 10 and 11. And then it keeps going like this, where it keeps identifying the 2 closest and merging them until you get a dendrogram or a tree that looks something like this. So again, I've taken the x values and y values and put them into a data frame. I've calculated the distance between those values, and then to perform hierarchical clustering I use the hclust command, and I have to apply that to a distance object that I calculated to get the distance between variables. Then when I plot that, I actually see this dendrogram. So you can see the 2 closest together points when I was doing the analysis, started off as 5 and 6. Then the next two closest together were 10 and 11, and so forth. And so at some point, the 10 and 11 point that got merged together ended up being merged with the 9 and 12 point that was merged together. And so that's why you see the dendrogram here. And eventually all of the points were merged together up at the top. So to see the distance between points, you actually have to traverse the whole length from 5 to 6. That's the distance between the points 5 and 6. And similarly, to go from 7 to 6, you have to traverse from 7 down here to 6. So what you can see now is that the hierarchical clustering has sort of grouped things into groups that are close together. You can see 5, 6, 7, 8 are close together, 9, 10, 11, 12 are close together, and 1, 2, 3, 4 are close together, sort of just like we expected to see when we generated the points. An important point here is that it just gives you the entire clustering dendrogram. It doesn't tell you which clusters things are broken into. So to decide what clusters things are in, you have to cut this tree at some point. So for example, if I cut the tree at 1 here, I see that they end up with 3 groups, the 3 groups that I originally started with. But if I cut, say, farther down here, say at 0.5, then I end up with more clusters. So I end up with 5, 6, 7 in a cluster, but it didn't cut 8 off separately, so it ends up in a different cluster. Similarly, when I cut off here at 5, I get 2, 3, and 1, 4 in different clusters as well. So basically, choosing where to cut this tree determines what the different clusters that you actually observe in the data set are. So you can actually make these dendrograms a little bit prettier. So I've actually included here a function. I think this is the best way to communicate it, although I'll also put it up on the class website. If you source this function into R, so you can actually just run this code in R, you get a new function called myplclust. And you can, instead of typing plot of your hclust object, you can type myplclust of your hclust object. And the reason why you would use this is because you can make dendrograms where you can color the leaves by a particular variable. So in this case, what I've done is I have this data frame. I again performed a hierarchical clustering. And now instead of using plot, I used myplclust of this hclustering object. And I've labeled the leaves using the lab parameter with the variables 1, 2, and 3. The first 4 values are 1, the next 4 values are 2, the next 4 values are 3. So those correspond to the original values that we generated in the 3 clusters. And then I can also make the colors be equal to, so I can use the parameter lab.color to be equal to the same clustering values. And so what I can see is now all the values of 1 are in black, all the values of 3 are in green, all the values of 2 are in red. And it makes it easier for me to visualize sort of the clarity of the different clusters and whether they actually cluster all the variables together like they should be. You can actually make them even prettier. So again, I've referred to the R graph gallery in previous lectures, but here's a link to a specific example from the R graph gallery where you can make sort of very pretty dendrograms that make it even easier to sort of communicate and to see information broken down by clusters. So the way that you can merge points together could be based on different distance metrics. So suppose that you're going to merge the points together in a clustering algorithm, and suppose we wanted to merge these 4 points in this top cluster with these 4 points in the bottom cluster. One way that you could do it is based on comparing their average distance, but another way that you could do it is based on comparing the points that are the farthest apart. This is called complete linkage, and it's one way of defining the hierarchical clustering algorithm. So when you tell it the method to use in hierarchical clustering, if you say complete, it will find the farthest distance between the 2 points before performing the clustering. Alternatively, we talked a little bit about using the average distance. So in this case, if you're going to merge these 4 points with these 4 points, you can actually take the average of their x values and the average of their y values and set it to be this point, and do the same thing for this cluster, and then compare those 2 values to get the distance between these 2 clusters. So it actually is quite depending on whether you use average or complete linkage clustering. You'll get very, very different clustering diagrams, and I encourage you to try out the different kinds of methods and see if they produce clusters that make sense. So another component of creating a hierarchical clustering is visualizing that clustering. One thing that you can do is actually visualize the quantitative data themselves after it's been clustered, and you can do that using the heatmap command. So again, I've created this data frame with the x and y values, And then what I'm going to do is I'm actually just going to take a small subsample of the columns here, or sorry, the rows here, so that it's a little bit easier to see what this plot looks like. And then if I run heat map on the sort of subsample data matrix, what it does is it actually clusters together, using that hierarchical clustering algorithm, it clusters together the rows and it also clusters together the columns. And so in this case, the clustering of the columns is not very interesting. There's only two values, x and y, two variables, x and y. But here, the sort of the observations of those variables, you can see that it clusters together the observations of those variables. And so for these sort of 12 subsamples, you can see what those clusters are. And it sort of visualizes the data themselves too, so you can actually see patterns in the quantitative data. And we'll talk more about using heat maps when we get to sort of analysis of specific data sets, particularly large dimensional data sets. So a few notes on hierarchical clustering. First of all, it gives an idea of the relationships between variables and observations, but the picture can be unstable. In particular, if you change a few of the data points or leave a few of the data points out, or if some of the data points have missing values, you'll get potentially dramatically different clusterings. And that's because by removing a point, you can actually change the which points are close to each other and how close they are to each other relative to all the other points in the picture. If you pick a different distance metric or a different merging strategy, as I mentioned, you'll get very, very different clustering algorithms out. And so it's very important to pick distance metrics and a merging strategy that correspond to the scientific problem that you're working on. And then if you change the scales of points for one variable but not for the others, so if you say standardize a particular set of variables but you don't standardize them for others, then you'll get very different results out. It is a deterministic algorithm in the sense that if I give the exact same data points to hierarchical clustering, it will always produce this, and I use the same distance metric and the same merging strategy, it will always produce the same dendrogram or the same merging structure. That won't be true, we'll see in a minute, for k-means clustering. Choosing where to cut the tree isn't always obvious. In our case, there was three pretty clear clusters, but in general, it won't be that easy. And so hierarchical clustering is often much more useful for visual exploration rather than for a more confirmatory analysis. I've linked here to a YouTube video where Rafa goes into some more details and an example about hierarchical clustering, as well as the Elements of Statistical Learning book, which has a lot more detail on both sort of applications and the mathematics of hierarchical clustering.